Hey, welcome. Ever find yourself just staring up at a jumbo jet, this massive 400-ton machine, and just think, how in the world does that thing stay up there? Well, that's exactly what we're going to solve today. We're going to unravel the mystery of how these incredible machines completely defy gravity.
I mean, it's a great question, right? It feels like it breaks every rule we think we know about the world. You take something like an Airbus A380. That thing can weigh over 1 million pounds, heavier than a blue whale. So how does it even get off the ground, let alone just hang out up there? The answer, it turns out, isn't magic. It's just some really cool physics, and we're going to walk through it piece by piece.
So, to figure this out, we've got to think like detectives. We're on the hunt for clues, but our clues are hidden in the laws of physics. And together, they're going to explain what seems totally impossible. Yeah, it really does seem impossible. A giant metal tube just floating in the sky. But it's not magic, it's physics. It's all about this elegant little dance between a very special shape and the air all around it. And that whole dance kicks off with our very first clue. Okay, let's get into it. Our first major clue, I'm just going to call it the squeezed air rule. Now, scientists have a much fancier name for it, but at its heart, it's all about one simple idea. What happens when you squeeze air and force it through a really tight space? So, that fancier name is the principle of continuity. The easiest way to get your head around it is to think about a river. You know how in a really wide, lazy part of the river, the water just kind of drifts along? But then, if that same river gets squeezed into a narrow canyon, whoosh, it rushes through like crazy. The same amount of water has to get through that tiny space, so its only choice is to speed up. Well, guess what? Air behaves in the exact same way. And this image here shows it perfectly. On the left, you've got this wide tube, plenty of space, so the air molecules are just cruising along nice and slow. But then, look at the right side. The tube gets narrow, it constricts, and to push the same amount of air through that much smaller space, it just has to speed up. There's no other way. That is the key idea right there. So, if there's one thing to take away from this, it's this super simple equation. Less area equals more speed. That's it. That's our first big clue in solving this mystery. So burn that into your brain, because we are definitely going to need it in a minute. And just as a quick side note, this rule is pretty much the bedrock for explaining lift, especially for planes that are taking off or landing, speeds up to about Mach 0.4. Now, once you start going supersonic and all that, things get way more complicated. But for understanding the fundamental secret of how a plane flies, this principle is exactly what we need. All right, let's grab our second clue. We've got the first piece of the puzzle down. Squeeze air and it goes faster. Simple enough. Well, our next clue comes from this brilliant 18th century mathematician, Daniel Bernoulli. And he figured out a fascinating connection between the speed of the air and one of its hidden properties, its pressure. Okay, so Bernoulli's theorem, it might sound complicated, but it's really all about energy. Basically, it says that for air that's flowing, its total energy is made up of two different kinds of energy. You've got pressure energy, that's kind of the air's potential to do work, and you've got its motion energy, which is, the energy from it actually moving. And the big rule is that total amount of energy has to stay constant. It can't just appear or disappear. And this table here lays out the trade-off perfectly. Check out the top row. When air is moving slow, it doesn't have much motion energy, right? So to keep the total energy constant, its pressure has to be high. It's like a seesaw. But now look at the bottom row. When that air speeds up, its motion energy shoots up. So for that seesaw to stay balanced, something else has to go down. And that something is its pressure. It's this perfect little balancing act. And this leads us to our second and maybe most important piece of the puzzle. It's a phrase you hear all the time in aerodynamics. Where the speed is high, the pressure is low. High speed, low pressure. It's the direct result of what Bernoulli figured out. Fast-moving air literally pushes less than slow-moving air. It's a game changer. Okay, time to put it all together. We have our two clues, our two puzzle pieces. Clue number one, if you squeeze air, it speeds up. Clue number two, when air speeds up, its pressure drops. Now, let's take these two ideas and apply them to the single most important shape in all of aviation, the airplane wing, or what engineers call an aerofoil. Just look at this cross-section of a wing. See how it's not just a flat board? It's got this very specific, very intentional shape. It's curved on the top, but it's much flatter on the bottom. And believe me, that special shape is the whole secret. It is literally designed to make our two clues work their magic. So to really see how this works, we're going to use a cool little thought experiment called a stream tube.
Just imagine that the air flowing over the wing is trapped inside an invisible, flexible tube. It's not a real thing, of course, but it's an amazing way to visualize what the air is actually doing as it splits and goes over and under the wing.
And here it is. This is the big aha moment. As the air flows over that curved top surface of the wing basically bulges up into our imaginary tube, right? And what does that do? It squeezes the tube. It makes it narrower. This is exactly what we saw with the pipe in our very first clue. It's the squeezed air rule, but in the wild.
So let's just follow the journey of the air for a second. It hits the front of the wing, the leading edge, and it has to split. Some goes over, some goes under. Now the air that takes the high road over that curved top gets squeezed into that tighter space. But the air that goes underneath, it's got a pretty straight, unsqueezed path. So what happens? The air on top has to speed up to get through that bottleneck. It's moving way faster than the air below. And just like that, we've pretty much cracked the case. We have now created a difference in speed. You've got fast air on top and slower air on the bottom. So now all we have to do is apply our second clue, Bernoulli's secret, and the whole mystery of lift is solved. Let's walk through the final steps. Okay, let's do the final recap. Step 1, the shape. That curved top of the wing squeezes the air. Step 2, speed. Because the air is squeezed, it has to speed up. That's our squeezed air rule. Step 3, pressure. Now we use Bernoulli's secret. That super fast air on top creates a zone of low pressure. And finally, step 4, lift. You've got high pressure underneath the wing pushing up and low pressure on top not pushing down as hard. The bottom wins. That difference in pressure, that imbalance between the push from the bottom and the weaker push from the top results in one thing, a net upward force. And that force, my friends, is lift. And as soon as that lift force becomes stronger than the weight of the airplane pulling it down, you're flying.
And there you have it. It's not magic at all, is it? It's just an incredibly clever, beautiful application of some fundamental physics. So now that you know the secret, that creating a difference in speed creates a difference in pressure, start looking for it. You'll see it everywhere. Why a baseball curves, how a sailboat moves against the wind. This principle of lift is all around us, hiding in plain sight.